The universe isn't a silent stage where galaxies perform. It is the stage, the very fabric beneath everything, stretching, drifting, pulling distances apart like a cosmic skin that breathes. And that simple fact, subtle as it may seem, has completely transformed the way we understand our place in the cosmos. Today, we'll travel through time and space to explore one of the strangest and most paradoxical truths ever discovered. The universe is expanding, not in the way trains pull away from a station, with galaxies flying apart, but in the space between them itself, the distance growing, the fabric stretching. But expanding into what? Does it have an edge? A center? And if it's expanding, then when did it start? Was there a real beginning? More importantly, will it ever stop? Or will it just keep drifting, cold and endless? Forever? Take a breath. There's no rush. We have time because time is just part of the story. And you, wherever you are, whether lying in a quiet room or lost beneath smeared city lights, are drifting along with that universe. So then, let's begin. Close your eyes and imagine you're living in Europe in the early 20th century. The city is still half asleep beneath a layer of morning mist. Horse-drawn carriages still share the streets with the new automobiles, and people, in their first modern dream, are beginning to believe that science can explain everything. And yet, the night sky remains a mystery. The stars still twinkle just as they always have. And perhaps that's why everyone believes the universe is unchanging. It has always been this way, and it will always be this way. No transformation, no expansion, no contraction, simply exists. When Albert Einstein completed his general theory of relativity in 1915, he didn't realize that the equations he had created would reveal something completely counter to the intuition of his time. In his model, space and time aren't a static backdrop where things merely unfold. They are a flexible fabric capable of bending, stretching, and warping under the influence of mass and energy. But something strange happened. When Einstein applied his equations to the entire universe, the result was that the universe couldn't stand still. It had to be either expanding or contracting. A dynamic universe, a living universe, and that troubled him. Einstein, like most scientists of the time, believed in a static universe. There was no reason to think it was changing. So, to keep his mathematical model aligned with this prevailing belief, he added a special constant, a subtle mathematical patch, to prevent space from expanding or contracting. He called it the cosmological constant. Just that, a number to keep the universe still. Everything seemed to be in order, until someone disagreed. Not far away in Belgium, a priest named Georges Lemaitre was studying similar equations. But Lemaitre was not just a priest. He was also a mathematician, a physicist, and, equally important, someone unafraid to question what seemed obvious. In a strange blend of religious faith and scientific passion, Lemaitre revisited Einstein's equations. And he let them speak for themselves. No edits, no patches, no cosmological constant, just the math laid bare. What would happen, he wondered, if we simply followed where the equations lead? And then he saw it. He saw a universe that was expanding, a space that stretched with every passing moment, a bizarre reality where galaxies drifted apart as though the very structure of space itself were being stretched. And if that were true, then going backward in time, the universe must once have been smaller, small enough to be a point, a primeval atom, as he called it, a beginning of everything. With no telescope, no experimental data, Lemaitre had only intuition and mathematics. In 1927, he published a paper dryly titled, describing an expanding universe, derived from limited astronomical observations and the logic of his equations. Few noticed, fewer understood. Einstein didn't reply. The idea was largely ignored, at least for the time being. But the sky has its own way of making itself heard. 4 years later, in 1929, at the Mount Wilson Observatory in California, a man named Edwin Hubble did what Lemaitre never had the chance to do: observe galaxies directly. With a giant telescope, he measured the distances and velocities of nebulae once thought to be part of the Milky Way. And then came a conclusion as shocking as it was clear. The galaxies were moving away from us. The farther a galaxy, the faster it seemed to be fleeing. It was as if the entire universe were inflating like a giant balloon. Not because galaxies were flying apart on their own, but because the space between them was expanding. There was no center, no edge. Every point in space saw all other points drifting away, just like raisins in a rising loaf of bread. This was the confirmation of what Lemaitre had seen in silence. This time, when Einstein heard Lemaitre present the expanding model, he no longer objected. In fact, he stood up, placed his hand on the Belgian priest's shoulder, and admitted, "This is the most beautiful and satisfactory explanation of creation I've ever heard." He also called his addition of the cosmological constant the greatest blunder of my life. But the story didn't end there, because if the universe is expanding, that means it must once have been concentrated in a single point. A moment of birth. An explosion not in space but of space. An explosion that would later be known as the Big Bang. That name started out as a joke. Astronomer Fred Hoyle, who didn't believe in the idea, mockingly said on a radio broadcast, "Oh, it seems we all came from a Big Bang." But the name, catchy and dramatic, stuck with the public. And from then on, the Big Bang became the symbol of the universe's origin. It seemed like everything was finally settled. But space always holds surprises. In the decades that followed, physicists kept digging. They discovered the cosmic microwave background, radiation left over from the early explosion. They found that the universe wasn't just expanding, it was expanding faster over time. And in trying to explain that, they had to bring back the very constant Einstein had once erased. The cosmological constant returned, this time with a new role, as a sign of a strange force pushing galaxies apart, what we now call dark energy. Strangely enough, a patch once considered a mistake became a doorway to one of the greatest mysteries of the modern universe. And at this point, you might be thinking, the universe is a mess. But maybe it's also incredibly consistent. A forgotten idea, a dismissed paper, a discarded constant, all return, like notes in a grand symphony we've only just begun to hear. When you look up at the night sky where the stars shimmer, you're looking into the very history of that idea. You're seeing light that left galaxies millions, even billions of years ago. And those galaxies are drifting away from you right now, not because you're special, but because the same thing is happening everywhere in the universe. The universe doesn't sit still. It doesn't stay quiet. It's expanding, silently, continuously, and irreversibly. And you, small as you are drifting along with it. A tiny planet in a spiral galaxy, swelling outward in an ocean of endless space. This is the beginning of a story, a bursting idea, and we've only just stepped into its first chapter. If you're lying still in bed, under a dim light, or leaning your head against the bus window on your way home, try this. Don't think about anything. Just breathe evenly, and picture the night sky again. Up there, on the dark canvas of the universe, tiny specks of light appear, each one a star. Some are near, some are far. Some stars have long since died, but their light is still traveling to us, like letters sent late from the past. Some of them belong to our Milky Way, the spiral home we live in, and some faint smudges, which might look like dust, are actually entire galaxies far away, each holding hundreds of billions of suns. Those galaxies are moving away from each other. That's what astronomers have discovered. A quiet but astonishing truth. But what makes it even stranger is this. They're not flying off on their own. Not like bullets from a gun. Not like planets thrown out of orbit. No one kicked them away. Instead, something invisible is expanding. And it's the very thing we're living in: space. That idea might sound wrong at first. Space. Isn't it just the emptiness between things? It's the background, the gap between you and me, between two planets, between two stars. How can emptiness expand? But that's the wonder modern physics has revealed. Space is not a dead void. It isn't static. It can bend, it can stretch, it can ripple like the surface of a pond. And what we see, the galaxies moving away from each other, isn't because they're traveling through space, but because the distance between them is being stretched by space itself. Imagine a loaf of raisin bread rising in the oven. As the dough expands, it stretches outward in all directions. The raisins don't move on their own, but the space between them increases because the dough is rising. They're pulled apart not because they're flying away, but because the space between them is growing. In the same way, as the universe expands, it's not because galaxies are rushing outward into some pre-existing emptiness. There is no outside. There is no space waiting for the universe to expand into. Space itself is expanding, like a surface being stretched in all directions, like an invisible rubber sheet, constantly and restlessly stretching. But that brings us to an even harder question. If space is expanding, what is it expanding into? Here's the catch. There is no outside. There is no space beyond the universe for it to grow into. Just like on the surface of the Earth, you can walk east forever and never fall off the edge. There's no border to fall from, no center to measure from, nothing outside for the universe to spill into. And that's what makes the idea of expanding space so difficult to grasp. Our minds, trained in a three-dimensional world filled with solid objects, are great at imagining things moving through space. But we're clumsy when it comes to picturing space itself as the thing that changes. Many people, when they hear that the universe is expanding, ask, so where is the center of the expansion? The answer is, there isn't one. Every point in space sees all other points moving away. And it's not because someone is in the middle, it's because space is expanding everywhere all at once. It's like blowing up a balloon with little dots drawn on the surface. As it inflates, all the dots move away from each other. There's no dot at the center, no special point. The expansion is uniform. Even you, if you could stay perfectly still and had a gigantic ruler to measure the distances between galaxies for hundreds of millions of years, would see that not only the faraway places are stretching. Everything is. It's just that on smaller scales, like Earth, gravity holds things tightly enough to resist that expansion. But across great distances between galaxy clusters, where gravity isn't strong enough to hold them together, space is free to stretch. And oddly enough, the farther away something is, the faster it seems to recede. That's what Edwin Hubble realized. When he measured the distances and speeds of galaxies, he found a pattern. A galaxy 2 million light-years away was moving away slower than 1 million light-years away. The speed of separation is proportional to the distance. A relationship as elegant as a simple equation. And so it became known as Hubble's law. But why does it work that way? Why does farther mean faster? One simple way to picture it is this. If space between every point is stretching at the same rate, then longer distances experience more total stretching. Like pulling a rubber sheet evenly at all points, the longer segments will stretch more than shorter ones. It's not that the faraway points are being pushed harder, but that there's more space between you and them, and each slice of that space stretches a bit. Add them all up, and the total expansion is greater. So the farther a galaxy is, the faster it drifts away. But this drifting doesn't mean it's breaking the speed of light, because no object is actually moving through space that fast. Space itself is stretching, and space can expand at any speed, even faster than light, without breaking any physical law. Because space doesn't carry information the way matter moving through space does. You can imagine space like a fast-flowing river. Leaves float along the surface. If the current flows faster than you can swim, you'll never reach the leaf ahead of you. No matter how hard you try, the distance increases. But the leaf isn't paddling away, it's just being carried by the flow. So if space can expand, can it also contract? Can it ever stop? That question remains open. But what we do know is that space isn't just expanding, it's expanding faster and faster. The rate of expansion is increasing, as if something invisible is pushing everything apart more and more quickly. That something is called dark energy, and it's one of the greatest mysteries in modern physics. But that's a story for another chapter. For now, let's return to the idea we've just begun to grasp. Space itself is a real, changing thing. It's not fixed, can stretch, can shrink. It can contain time, light, planets, and questions we haven't yet answered. You're living in a gigantic loaf of raisin bread that's rising. But you're also a special raisin, aware that it's being stretched along with all the others. And maybe the most beautiful thing is, you can stand still, look up at the sky, and know that the distance between you and those stars is changing, even though you haven't moved at all. Space is expanding, and you, a part of that space, are drifting along with it. Slowly, invisibly, silently, like a classical melody you can only feel when you sit very, very still. A quiet question echoes through every night of stargazing. If the universe is expanding, how fast is it expanding? It's like standing on the beach and watching the tide rise. The next question is always, how quickly is the water rising? You might not need an exact number, just a feeling. But if you're a scientist, a feeling isn't enough. You need a number. You need measurement. That's the nature of astronomy, beautiful but not something you can just look at and believe. Starlight is all we have. And from those tiny points of light, we've learned how to read velocity, distance, age, and even the motion of galaxies beyond imagination. When Edwin Hubble discovered that galaxies were moving away from us, he also found something special. The farther a galaxy was, the faster it was receding. The greater the distance, the greater the speed. It wasn't random. It was a law, a relationship between distance and velocity. The formula he came up with seemed almost embarrassingly simple. V equals h times d, where v is the recession velocity of a galaxy, d is its distance from us, and h is a constant later called the Hubble constant. Those three dry-sounding letters h are actually among the most important numbers in cosmology. They tell us how fast the universe is expanding right now. It's the heartbeat of space, the gentle sigh of a growing universe. But to know how much h is, we need two things: the distance to galaxies and their speed. Speed is the easy part, relatively easy. Just look at the shift in the wavelength of light, what's called the Doppler redshift. If a galaxy is moving away, its light stretches, shifting toward the red end of the electromagnetic spectrum. You look at a light spectrum, measure the shift, and you have the speed. But distance is a whole other story. How do you know how far away something is if you can't get close, can't touch it, can't measure it directly? In the universe, you don't have measuring tapes, no maps, no GPS. All you have is light. And yet somehow, with incredible patience, humans figured it out. They built a cosmic distance ladder, a step-by-step system of measuring techniques, moving from nearby to far, climbing the rungs of light. The first rung is the moon and the planets in our solar system, measured using trigonometry, radar. From there, we calculate the distance to nearby stars using parallax. As Earth orbits the Sun, the apparent position of a star shifts slightly, and from that we calculate distance. Next come variable stars, especially a type called Cepheid variables, stars that pulse in a steady rhythm. The amazing thing is that their intrinsic brightness is related to their pulse period. If we know how bright a star truly is, and compare it to how bright it looks from Earth, we can calculate its distance, just like judging how far away a light is based on how dim it seems. Now you have a ruler, and you start stretching it farther, measuring the distance to galaxies that contain Cepheid stars, then even farther beyond. And then you reach type Ia supernovae, explosions of white dwarf stars that follow a pretty consistent pattern. Because they explode with almost the same brightness every time, they become cosmic lighthouses. Spot a type Ia supernova in a distant galaxy, and you can measure how far away it is. At that point, you have both things, redshift speed, supernova distance, and you can calculate the Hubble constant. But of course, it's not that simple. In the 1990s, estimates of h varied wildly, from around 50 to 100 kilometers per second per megaparsec. 1 megaparsec is over 3 million light-years. That means for every extra 3 million light-years of distance, a galaxy moves away faster by 50 to 100 kilometers per second, depending on who measured it. That's a huge spread for such an important number. So scientists got serious. They brought in bigger telescopes, more precise data. By 2011, Two independent research teams measured H using supernovae and came to roughly the same result, about 73 kilometers per second per megaparsec. A solid number. Stable. It seemed like we'd finally nailed down the expansion rate of the universe. But then, the wall started to shake. Another group didn't look nearby, but instead looked way back at the cosmic microwave background. And they got a very different result. The cosmic microwave background is ancient light left over from when the universe was just a few 100,000 years old. It holds delicate imprints, tiny ripples caused by uneven matter density. From those ripples, using complex mathematical models, you can predict what today's Hubble constant should be, if the universe follows the physical laws we believe in. And the result? About 67 kilometers per second per megaparsec. A sizable gap from the 73 that nearby measurements gave us. This isn't just a margin of error. This is a real and serious conflict. If different methods, different data, and valid physics models all point to the same truth, they should all land on the same number. But right now, they don't. The discrepancy is too large to be explained by statistical noise. It's a gap so big it has its own name, the Hubble tension. Tension, not in the emotional sense, but a pulling between two different ways of understanding the same universe. This could mean one of two things. Either one of the methods is wrong. Maybe the supernova measurements aren't as accurate as we thought. Maybe there are systematic errors we haven't accounted for. Or maybe the interpretation of the cosmic microwave background is flawed, based on faulty assumptions. Or both are right. And if both are right, then our model of the universe is missing something. Maybe an unknown particle, a strange form of energy, a change in how the universe expanded over time, something no one's seen, a ghost hiding in the numbers. And that's where cosmology becomes detective work. When the data is clear, but the logic doesn't line up. When you know something is wrong, but you don't know what it is yet. Physicists call it a hint of new physics, like a hairline crack in the wall that could lead to a major breakthrough. Every time there's been an unexplained disagreement, physics has responded with a revolution. Relativity started that way with a question about how fast light moves. Quantum mechanics, too, began with a mystery about light coming from hot metal. Now, the question is, how fast is the universe expanding? And why can't we agree on the answer? You might think this is a physicist's problem, but it's not. It's all of ours because you live in that universe, too. You're also drifting along with space as it stretches. And you're also facing a future we can't predict, because we don't yet know how space is truly changing. A difference of just a few kilometers per second per megaparsec might seem small, but stretched over billions of light years, it could mean a universe that expands forever or tears apart. A universe that cycles or ends in a final rip. Every theory hinges on that number, and that number still isn't agreed on. When you look up at the dark night sky, you may not think about it. But in the dim glow of distant galaxies, tiny fluctuations are hiding pathways that lead to different versions of the cosmos. And if you listen long enough, you might feel something strange. The universe is not just expanding, it's hesitating, as if it's keeping a secret right there among the numbers. Imagine you're walking across a flat field under a deep, dark night sky. Ahead of you is a bright star. You walk toward it step by step, but you'll never reach it, because that star is millions of light years away, and the light you're seeing comes from a distant past. Still, even though you can't touch it, you know you're moving, traveling through space. The question is, what is the actual shape of that space? From the beginning, humans have imagined the universe as something that's inside something else. Earth is inside the solar system. The solar system is inside the Milky Way, and the Milky Way is inside the universe. But then a quiet question appears. What is the universe inside of? Does it have an outside? Does it have an edge? And if it does, what's beyond that edge? Nothingness? Another dimension? An endless white void? These questions aren't easy to answer because first, we have to understand what space really is and how it can bend. In 1915, a man with messy hair, who often forgot his keys and had little patience for journalists, changed the way we see space forever. His name was Albert Einstein. Einstein didn't see space as a fixed stage where matter plays its part. He said space and time themselves are part of the play, something called space-time, which can be stretched, curved, and distorted by the very matter and energy it holds. You no longer needed a mysterious pulling force to keep planets orbiting the sun, as Newton imagined. Instead, according to Einstein's general theory of relativity, the sun's mass bends the space-time around it, and Earth simply follows that curved path, like a marble rolling along the inside of a bowl. Space, to Einstein, was no longer flat, could bend. And not just around stars and planets, the entire thing could be curved. The whole universe. It sounds abstract, but the idea is actually quite familiar. Imagine you live on a sphere like Earth. If you walk straight forward forever, you won't fall off an edge because there is no edge. You'll eventually circle back to where you started, never having seen the outside of Earth. You're living in a curved space, a positively curved space. Now imagine living on an endless flat surface like a tabletop. That's flat space. Or maybe you live on a giant saddle, curving away in two directions. That's negatively curved space. These three geometries, flat, positively curved like a sphere, and negatively curved like a saddle, are the three ways the universe could be shaped on a large scale. And for decades, cosmologists have tried to answer, which one are we in? The answer doesn't come from how we feel, but from light. When space is curved, light doesn't travel in straight lines, or rather, what looks like a straight line in curved space becomes a curved path to us. Just like how planes fly straight across the ocean, but appear to curve on a flat map. Astronomers measure the shapes and distribution of distant galaxies, galaxy clusters, and especially the cosmic microwave background, the ancient light left over from the early universe. By analyzing the tiny ripples in that light, they can infer the curvature of space. And so far, the result seems to be the universe is nearly flat. Not perfectly, not absolutely, but on the largest scales, the geometry of the universe doesn't appear to curve in any major way. That's a big deal. It tells us that the total amount of matter and energy in the universe is very close to a specific critical value, the tipping point. More than that, and the universe would curve positively. Less, and it would curve negatively. It's like balancing on a knife's edge. Lean just a bit and you fall to one side. Yet somehow our universe is balanced on that edge. Why is that? That question leads to another idea, cosmic inflation, a period of ultra-fast expansion in the very first instant after the Big Bang, which smoothed out any original curvature, like how a balloon becomes rounder as you blow it up. But even if the universe is flat, it still might have no edge. Let's go back to the sphere. Its surface is two-dimensional with no edges, yet it's finite. You can keep walking and never exit. If our three-dimensional universe is like a 3D surface of a sphere, it could be finite, with no edge, no rim, and still have no outside. And then comes the age-old question, what is the universe expanding into? The surprising answer is, it doesn't need to be expanding into anything. Just like when you draw an expanding circle, you don't need a bigger sheet of paper to contain it. It's the coordinates themselves that are changing over time. The universe isn't growing into a larger space. The space itself is what's growing. That's what makes cosmological thinking so different from everyday intuition. In daily life, when we say something expands, we assume it's expanding into something. But in the universe, that surrounding container doesn't exist. The universe is everything. There is no outside. Space isn't inside anything else. Space is its own thing, and it can bend, shrink, or stretch without needing an edge. So is there an edge to the universe? The answer, as far as we know, is no. Whether the universe is finite or infinite, flat or curved, there's no evidence of an edge. No final wall, no end, where space suddenly stops. If you flew in one direction forever, you would never hit a border. You would just keep going endlessly, never arriving. This also leads to another strange thought. If there's no edge and no center, then every point in the universe is equally valid. There's no center of the Big Bang. No single starting spot. Every galaxy sees other galaxies moving away. Every observer, no matter where they are in the universe, can believe they are at the center. And they wouldn't be wrong. That's the strange thing. A universe with no center, yet everywhere can be the center. Perfect symmetry, a profound humility in space itself. And so, when you quietly look up at the sky, you might start to imagine. Those stars aren't just scattered in a still, flat space. They're flying apart in a soft, flexible space. One that can bend, that can stretch, that might even fold back onto itself. Space isn't just a fixed background. It's a living character in the cosmic play, a curtain that ripples to the rhythm of gravity. Space curves and light bows along with it. Time slows near great masses. Things that once seemed impossible become law. And the images you see in the sky, those arcs of light, those shimmering ghosts bent by massive objects, are all traces of a flexible space. Space is the stage, the storyteller, the dream with no ending. And maybe, as you lie down in the dark, beneath a gentle breeze and the wide-open sky, you might feel the faint curve of something invisible, a soft line of space, where light twists and time forks. The universe is not just expanding. It's also folding gently around the questions we haven't yet answered. Have you ever wondered, if the universe really began with a massive explosion, a brilliant, fiery starting point, then where is the light from that first moment now? Is there anything left? A faint glow, a lingering echo, a blurry mist, from the instant time itself began to flow? The answer is yes. And strangely enough, that light still surrounds you. Right now, everywhere. Not dazzling, not blazing, but quiet, like a steady, gentle breath, stretching from the dawn of time to this very moment. It's called the cosmic microwave background, or CMB. This is the oldest light we have ever seen. A snapshot from the moment the universe first became transparent, when light was no longer trapped in a thick fog of plasma, but free to travel across space. To understand why this matters, we need to go back to the beginning, about 13.8 billion years ago, just a few 100,000 years after the Big Bang. Back then, the universe was a blazing fog. Everything was so hot that atoms couldn't exist. Electrons and protons floated around, crashing, bouncing, colliding and scattering. Light couldn't travel far, it kept slamming into free particles, getting absorbed and re-emitted. The universe was like a room thick with smoke and fire. You couldn't see more than a few steps ahead. But then, like an early morning when the fog begins to lift, the universe cooled. When it dropped to about 3000 Kelvin, electrons and protons finally settled down together and formed neutral hydrogen atoms. And just like that, light was free. It escaped the plasma fog and began its journey outward. That moment is called the photon decoupling era, and the light from that time, after billions of years traveling through an expanding and cooling universe, has now cooled to just about 2.7 Kelvin. It's no longer visible light, but microwave radiation, soft, invisible waves, gently weaving through every corner of the cosmos. In 1964, two radio engineers, Arno Penzias and Robert Wilson, were tuning an antenna for an experiment in New Jersey when they stumbled on a strange type of noise. Came from every direction. Couldn't be blocked. It didn't change with the day or night. And most importantly, it never went away. They tried everything. Cleaning bird droppings off the antenna, changing its direction, swapping out equipment, but the signal remained. They didn't realize they were hearing the echo of the Big Bang. Another group of cosmologists working at Princeton University had predicted the existence of the CMB earlier. And when they heard about Penzias and Wilson's discovery, the final puzzle piece fell into place. This was the strongest evidence yet that the universe had once been hot, dense, and glowing like fire. The Big Bang was no longer just an idea. It became something real, something you could detect with your ears, or rather, with an antenna and a microwave receiver. And that was the first great wonder. The ancient light is still here, still telling the origin story of the universe. But something else amazed scientists when they listened more closely. The cosmic microwave background is almost perfectly uniform. No matter which direction you look, the temperature of the microwave radiation is nearly the same, differing by only about 1 part in 100,000. No side is significantly hotter, brighter, or earlier. And that's weird, because how could regions of space, separated by billions of light years, know to match temperatures so closely? How did they share information, agree on a temperature, when light didn't have time to travel between them? This question led to one of the most important theories in modern cosmology, the theory of cosmic inflation. According to this theory, in the very first moment after the Big Bang, just a few millionths of a trillionth of a second, the universe expanded faster than the speed of light, which is allowed, since it was space itself expanding, not anything moving through space. That inflation stretched a tiny, thermally balanced region into the entire observable universe. That's why everything has the same temperature, because it all came from the same place before space ballooned outward. But not everything is perfectly smooth. When satellites like COBE, 1992, WMAP, 2001, and later Planck, 2013, were launched to listen to the CMB in finer detail, they discovered that it wasn't entirely uniform. There were tiny ripples, tiny temperature fluctuations, only a few parts per million. But those ripples, too small for your skin to even feel, were the seeds of everything in our universe today. They were the slightly uneven patches, where a little more matter gathered, where gravity could take hold, pulling in more and more. Over time, those denser areas grew into galaxies, galaxy clusters, and the enormous cosmic web we see today. Without those ripples, if the CMB were perfectly smooth, the universe today would be just a featureless fog. No stars, no planets, no people. That means everything from galaxy clusters to you began as tiny fluctuations in the ancient light. There's something humbling about looking up at the night sky and realizing the most beautiful light is also the oldest. The CMB doesn't shine, it doesn't dazzle, but in that quiet presence, it holds the memory of the universe, like a faded photo from its childhood. It doesn't tell stories of stars or planets, but of the moment before anything existed. It's like holding an old photo of yourself, a tiny newborn, eyes shut, unaware of your name, and from it, understanding that everything you've become began right there. The CMB is that photo for the universe. Faded image, but accurate. Almost flat, but with a few tiny creases, just enough to form everything you see today. If you've ever asked yourself, did the universe really start from a hot, dense point? If you want evidence, not belief, then the cosmic microwave background is the answer. Not mystical, not abstract, but a real, measurable signal, one we can photograph and map. Something you can actually hear with an antenna. Light that old TVs used to pick up as static when no channel was tuned in. The last glowing dust from the dawn of time. And that's the most amazing part. The first light hasn't disappeared. It's just whispering, slowly, softly, steadily, like the whisper of time itself. Do you remember when we talked about the cosmic microwave background, the lingering light from the dawn of time? We saw how strangely even that light was, as if every corner of the universe had once been one. As if the entire cosmos had once shared a warm cup of tea, then wandered off in different directions on a cold winter night, yet still held onto the same warmth. That, by normal logic, should be impossible. Because if light, the fastest signal in the universe, never had time to travel between those regions, how could they have agreed on the same temperature? The answer didn't come from a star or some bizarre measurement. It came from an idea, simple yet bizarre. The universe once expanded faster than the speed of light. The cosmic inflation hypothesis. In the early 1980s, a young physicist named Alan Guth was wrestling with some inconsistencies in the Big Bang theory. He wasn't trying to rewrite all of cosmology, just fix a few small gaps. But like all big discoveries, those small gaps opened up a massive doorway. Guth asked a simple question. What if, in the very first instant, space expanded at a superfast rate? Not gradually, not slowly, but in a sudden blow-up, where a tiny speck of the early universe was stretched millions or billions of times in just 10 superscript 3 seconds. This wasn't an explosion, it was inflation. Like when you suddenly blow into a balloon, and it swells so fast it blurs anything drawn on its surface. No sound. No light. Just space itself, the fabric of the universe, stretching faster than light could ever travel. And strangely enough, that doesn't break any physical laws. Because according to relativity, nothing can move through space faster than light, but space itself isn't bound by that rule. It can expand like a fabric being pulled, and that's totally allowed. Inflation and the strange uniformity of the CMB. Goose realized that if the universe did go through such a phase of inflation, then tiny regions that had already reached thermal balance would have been stretched to cosmic scales. The result? Every spot we see in the CMB today, though they appear far apart, were once right next to each other. They exchanged light, shared warmth, and equalized their temperatures. Like friends gathered around a fire, flung across a room but still feeling its warmth on their skin. Inflation explains that beautifully and simply, something the original Big Bang Theory could never do. And not just that, it explains a lot of other mysteries we've observed but never fully understood. The universe's strange flatness. When you look at the universe on a large scale, you'll see space is almost completely flat. This means if you drew a giant triangle with beams of laser light, each side stretching billions of light years, the total of its angles would still be about 180 degrees, just like in old-school Euclidean geometry. But how could the universe be that flat? Just a slight difference in the initial mass density would have curved it dramatically, either positively or negatively, sending everything in a completely different direction. Again, the answer lies in inflation. If you stretch a small patch of surface, even a slightly curved one, into something enormous, it becomes flatter and flatter. Like standing in the middle of a massive balloon, you'd only see flat ground, even though it's curved. Inflation didn't just blow up space. It smoothed out all the wrinkles, leaving behind a shockingly flat canvas. False vacuum and the birth of inflation. Goose proposed that inflation was powered by a special kind of energy, found in something called a false vacuum. In quantum physics, not all vacuums are equal. Some are lower in energy than others, but to move from a false vacuum to a true one, you have to cross an energy barrier. While the universe was stuck in this false state, rich in energy, stable but not permanent, it expanded incredibly fast, like a balloon swelling under internal pressure. Then it collapsed, shifted into a lower energy state, and all that excess energy turned into matter, light, and heat. The Big Bang, in the traditional sense, may have been the end of inflation, not the absolute beginning. A bubble universe in a cosmic ocean? But Goose and many other physicists didn't stop there. If inflation happened once, why not more than once in different places? Like soap bubbles forming in a boiling pot of water, every patch that transitioned from a false to a true vacuum could have created its own universe. Each universe might have different physical laws, different constants, different structures. And so, the idea of the multiverse was born. In this view, our universe is just one bubble in a vast cosmic ocean, where countless other bubbles are forming, growing, colliding, then drifting off into the infinite unknown. We can't see these other universes because light can't reach us from them. But if the idea is true, then everything we know, physics, space-time, is just a local rulebook, not an eternal truth. And if that's so, then what came before the Big Bang? That ancient question, long forbidden in traditional physics, suddenly became valid. If the Big Bang was merely the end of inflation, then something else existed before. Maybe it was a false vacuum. Maybe a parent universe. Maybe some bizarre quantum phenomenon no one understands yet. We don't know. But at the very least, inflation opens a door, not just to explaining our universe, but to imagining what lies beyond. It turns the beginning into just one chapter in a much longer, deeper, wider story. Imagine standing in the middle of an endless field. You can't see where it began, and no edge is in sight. The breeze is soft. The grass sways. You think you're at the center, but where is the center of something with no borders? The universe is like that, and maybe other fields with other winds, other rules are drifting through the invisible realm, far beyond your view. Inflation isn't just a beautiful theory, it's left behind testable traces. Patterns in the CMB, the distribution of galaxies, primordial gravitational waves, All are places where inflation may have whispered its presence. And though many details remain unclear, the overall message still rings out like an ancient poem. The universe, in its very first moment, took one long, deep breath. A breath that stretched space into oceans, light into song, and everything into the world we now see. There was a time when people believed the universe was slowing down. The reasoning was simple. If the universe is expanding, and if all galaxies pull on each other through gravity, then over time, that expansion should slow down. Like a ball thrown into the air, it moves quickly at first, but eventually, Earth's gravity pulls it back, slowing it down and bringing it down. The universe, it seemed, should behave the same way, expanding more slowly over time. Depending on how much matter it contains, it would either continue expanding but more gradually, or eventually stop and collapse in a fiery death. A big crunch. But in 1998, two independent teams of scientists discovered something that shook the entire world of physics. Not only is the universe not slowing down, it's speeding up. Distant supernovae, used as standard candles to measure distance, appeared dimmer than expected. That could only happen if their light had traveled through a universe that was expanding faster and faster, stretching the space between the source and the observer more than anyone had imagined. And so, something absurd became reality. There is something invisible out there, quietly pushing the universe apart, tearing at the seams of space, making the distances between galaxies grow faster and faster with time. Something that doesn't act like gravity but acts against it. Something that isn't matter, doesn't shine, can't be touched, can't be named, yet makes up nearly 70% of all the energy in the universe. We call it dark energy. Not dark because it's black, but because we don't know what it is. All we have is its effect on the scale of the universe. A strange effect. Instead of pulling things together, it pushes them apart. It's unlike any force we've ever known. Unlike dark matter, which is also invisible, but still interacts through gravity, dark energy doesn't clump like matter does. It spreads evenly across all of space, as if every point in the universe wants to drift away from every other point, gently but relentlessly. Some physicists think dark energy might be the cosmological constant, something Einstein once added to his equations in 1917 to keep the universe static. At the time, he believed the universe couldn't change, a common belief then. To counter gravity in his equations, he added a small constant, a subtle push to hold everything in place. But when Hubble showed the universe was expanding, Einstein regretted it and called it the biggest blunder of my life. Ironically, that blunder might have been right. If dark energy really is a cosmological constant, unchanging over time, then it's a form of energy that is built into the fabric of space itself. A kind of reverse pressure. The more space there is, the more dark energy exists, and the more expansion it causes. A feedback loop that can't be stopped. But there are other ideas. Maybe dark energy is a dynamic energy field, something physicists tentatively call quintessence, a kind of fifth essence beyond the four fundamental forces: gravity, electromagnetism, the weak force, and the strong force. In this model, dark energy could change over time, grow stronger, or even disappear. But so far, we haven't found any sign that it's changing. One way or another, dark energy is now the ruling force of the cosmos. In the early universe, matter, both ordinary and dark, still had the upper hand. Gravity was strong enough to form galaxies, clusters, and large-scale structures. But as space expanded, matter became more diluted, while dark energy, unaffected by volume, began to dominate. And for the past 5 billion years or so, the universe has been in an era of accelerating expansion. And now we face a haunting question. If this keeps going, what will happen? The first scenario, one currently supported by observations, is the so-called Big Freeze. In this future, the universe keeps expanding forever, faster and faster, until galaxies are moving away from us faster than the speed of light. The cosmos grows emptier and colder. The last stars burn out. Black holes slowly evaporate. And after trillions of years, only isolated particles remain, drifting in a universe nearly frozen. A quiet, lonely death. But if dark energy isn't a constant, if it's growing, then the future could be even more terrifying. In the Big Rip scenario, dark energy becomes so powerful that it doesn't just push galaxies apart, but rips galaxies themselves apart, then solar systems, then planets, then atoms, and finally, space-time itself. A death not just cold, but violent, tearing everything into nothingness. Right now, no one knows which scenario will come true. We're still measuring, still listening, still watching for tiny deviations in ancient light to understand the true nature of what's pulling the strings of the universe. A few space telescopes, like Euclid and the Nancy Grace Roman, are scanning the skies, not looking for new stars, but for a darkness. A darkness we can't see, but always feel in the way space stretches. It's a paradox, isn't it? Our universe, filled with hundreds of billions of galaxies, millions of trillions of stars, and who knows how many worlds that might host life, is ruled by something we don't understand. Something we can't touch, can't taste, can't capture, but that holds the power to shape the future of all existence. And perhaps the strangest thing is this: we, born from stardust, standing on a small planet orbiting a rather unremarkable star, are able to ask questions about the very force shaping the destiny of the cosmos. Maybe we don't have the answer yet, but the act of asking, the courage to look into the void and admit we don't know, is the first step to knowledge. The universe is expanding. More than that, it's accelerating. No one knows where that will lead us. But when we look up at the night sky and feel the light from galaxies billions of light years away, perhaps we are also looking into the past and the future, a future stretched by an invisible hand, a silent push, something waiting to be understood. When you stand under the night sky and look up at the stars, you might not be thinking about the future. What you're really seeing is the past, light from distant galaxies that began its journey millions, even billions of years ago, just now reaching your eyes. But that sky is also a mirror, reflecting the fate of the universe, quietly tracing out the possible paths that space and time may follow. The universe is expanding, and not just expanding, but expanding faster and faster. This much we know. We can measure it, calculate it, observe it. Our silent telescopes search for dying candles, distant supernovae, and tell us that space is growing larger than we ever imagined. But what we don't know, what no formula, no machine, no extrapolation can yet reveal, is the ending. This universe we live in, where is it going? It may keep expanding forever. No pause, no slowing down, no collapse. Just ever-growing distances between everything, until the light from the farthest galaxies dims and vanishes beyond our reach. Galaxy clusters close to each other will become isolated cosmic islands, each one a fading mini-universe surrounded by thickening darkness. Stars will die. Black holes will slowly evaporate through Hawking radiation. And eventually, only lone particles will remain in an icy, endlessly expanding void. A quiet, stubborn death known as the Big Freeze. But that may not be the darkest ending. If dark energy, the mysterious force causing this accelerating expansion, isn't constant, but increases over time, then an even more terrifying future awaits. In a scenario called the Big Rip, dark energy grows stronger and stronger, surpassing gravity, even tearing apart the nuclear forces that hold atoms together. Not only will galaxies be ripped from each other, but galaxies themselves will be shredded. Stars, planets, people, atoms, all stretched, torn, and broken into nothing. Nothing will survive. There will be no time to notice the end, because even time will be destroyed. A violent, abrupt finale, as if the universe tears itself apart with the very force that once gave it life. Still, some cosmologists don't believe in endless expansion. They wonder, if the universe can expand, could it also contract? If there's enough matter, visible and invisible, gravity could one day halt the expansion and pull everything back to a single point. A big crunch. The universe began at a singularity. Could it also end in one? And if it does, what's to stop a rebirth? Could a collapse lead to another explosion, a big bounce, a new universe rising from the ashes of the old, like a phoenix? like a giant pendulum swinging between extremes. Expanding, contracting, expanding, contracting. The universe might have no single beginning, no single end, just an endless cycle, a cosmic rhythm beyond any human lifespan. But the truth is, we don't yet have enough data to know if the universe has enough mass to fall back in on itself. And dark energy, the deciding factor, remains a silent mystery at the heart of our incomplete equations. While we wait for answers, there's something stranger than any scenario. The moment we're living in right now. This might be a uniquely rare chapter in cosmic history. Galaxies are still close enough to see. Light from the early universe, like the cosmic microwave background, is still detectable. Space hasn't yet stretched so far that light disappears. Black holes haven't evaporated. Stars are still being born. And we, tiny, intelligent creatures on a planet circling an average star, are able to ask, how did the universe begin? And how will it end? Imagine a future civilization living in an isolated galaxy cluster, where all other galaxies have passed beyond the cosmic horizon, where there's no trace left of the microwave background, where the night sky is no longer thick with stars, only a few faint lights in deep darkness. To them, the universe might seem still, unchanging, no expansion, no Big Bang, no cosmic history. They will never know what once was, because the evidence has traveled beyond light's reach. We, in this moment, are living in a cosmic observation window, a miraculous time when physics, measurement tools, and curiosity align to unlock great truths. An age when humanity, a species of clever, flawed primates, can sit beside a telescope, listen to echoes from the beginning, and gaze toward a distant future with a fearless mind. Maybe the universe will freeze, explode, collapse, or quietly fade away. Maybe we're just a brief dream in an endless timeline. Maybe there will never be a final answer. But in this moment, the one you're in right now, listening to these words, one thing is certain. You are alive in a changing universe. An expanding universe. A universe with a history, a beginning, and possibly an end. And you, in the middle of all that uncertainty, have the capacity to think about it. Not just to know, but to understand that you are part of something greater than words can hold. The universe may be going somewhere or maybe nowhere at all. But with every question we ask, every measurement we make, every time we look up at the sky, we lay down one small stone on the path toward meaning. Not to control the universe, just to feel less alone in a space that stretches forever. The end may be waiting far ahead, but understanding always begins here. The universe has no edge. There is no wall where space ends, no door at the end of time. Only expansion, silent, continuous, all-encompassing. Like a breath that never stops. Like a song with no final note. No one knows what lies ahead. No one fully understands what came before. But we keep drifting. Every speck of dust, every star, every unanswered question, moving along that invisible current. And you, no matter how small, are part of that story. Not an outsider, not a bystander, but an inseparable piece of the universe unfolding to the rhythm of its own heartbeat. You are one beat in that expansion, a fragile light in the eternal night, but real and meaningful. So, just close your eyes. Imagine yourself floating in stillness, where there's no up or down, no before or after, only the gentle drift of space stretching out around you. You don't have to understand it all. Just feel it. You are here, in a vast, strange, impossibly beautiful universe. And you, yes, you, are part of a miracle that's expanding forever,